Great. So today I wanted to tell you about a project I've been working on and off for some time now, thinking about how to use double categories and double categories with additional structure to think about what people have called like categorical doctrines. So like, in other words, a way of systematizing the description of categories with extra structure, like monodal categories or symmetrical monodal categories or Cartesian categories and so on. And I actually have a really sort of like concrete and long-lasting reason to be interested in this sort of thing, which is that one of the things that we have in the software package CatLab as a kind of organizing principle is a way of describing different kinds of categories with structure. And we have been using something called generalized algebraic theories for that. So those are basically, or GATs, as we call them for short. And so the GATs are basically the minimal extension of algebraic theories with like some kind of dependent type theory. And that suffices to express the theory of categories, whereas like an ordinary algebraic theory does not. And you can also express two categories and all sorts of other things. And so that's fine enough, but I've never really been that satisfied with it because GATs are in a sense both too general but also not general or powerful enough. So they're too general in the sense that like that they can describe dependent type theory of like sort of arbitrary depth. So like you can express all sorts of higher categories and stuff in them, but they don't know about the higher categorical structure. So like for a given GAT, you have a category of models, which in the case of categories would give you, the theory of categories would give you like categories and functors, but where are the natural transformations? It doesn't know about those. So somehow it's not really a system for working. It's not a system for working with categorical structures. It's a system for working with dependently typed algebraic theories. So I've wanted something sort of more intrinsically categorical. The conventional way of, as I understand it, and I'm not an expert on this stuff, but the conventional way, as I understand it, of talking about so-called doctrines is with two monads on cat, kind of like you can talk about algebraic theories if you want by like finitary monads on set. And that approach I think is somewhat developed, but it's like not very, it's hard to get your hands on it. Like if you want to program it, how do you write down a two monad on cat? I don't know. I mean, it seems hard. So what I'm really interested in is a system for talking about doctrines where you can present them by generators and relations, just like you can present an algebraic theory or Lawvere theory by generators and relations. And so that's kind of what I want to tell you about. And at some point, it occurred to me that double categories are actually a really natural place in which to do that. And I want to try to explain that, convince you of that. And I guess as a final caveat before I really get started, this is very much a work in progress talk. There are certain things that are not finished. There are certain things that I don't know the answer to. I'm giving this talk largely because I want to hear your thoughts and get your feedback. So feel free to interrupt me if things aren't making sense. And I'm also happy to have discussion afterwards. Okay, so I'm going to assume that you've at least probably seen double categories before somewhere, so I'm not going to start with the definition of a double category, but I will sort of fix the notation. So the viewpoint that is nice for double categories is to think of a double category D as being a category, or to be more precise, a pseudo category internal to cat. So you have two categories, D1 and D0, with source and target morphisms between them. You have a composition, an external composition, and an identity that obey the laws of a category, or more precisely a pseudo-category. So the motivating picture for me, though, is this. So like, why double categories for this? Well, the way I like to what this description of double categories is suggestive of. So let's remember that, like, in a cell, so in the highest dimensional thing, cells are morphisms in D1. So you know, let's say we have like so this whole thing is an object in D1. So it has source and a target. Oops. Yeah, thanks. Yeah, I did both at the same time. Okay, and similarly, you know, alpha has. Okay. And so the fact that, so the things in the vertical direction I'll call arrows, the ones in the horizontal direction I'll call pro-arrows. The way that this picture makes you want to think about pro-arrows is that they're actually not really, they're actually objects in D1. So that happen to have a source and a target. Whereas like the things that are really thinking of morphisms are the arrows and then the cells, which are going from M to N. And so the idea then is that, like, the horizontal part of this double category really is like, it has the type structure, precisely the type structure that you need to talk about like the theory of categories. Because, you know, if you have you could have an object X and then a pro-arrow from X2 itself, which we think of as like morphisms. So, and then you can also do the essential things that you need to do to write down the theory of categories, and that's what I'll say next. But what I want to just convey now is that, like, we're going to think about the horizontal part as being like the dependent type structure, which is specific to sort of categories, and then the horizontal direction is being mappings on objects and then compatible mappings between morphisms. Does that sort of make sense as a motivation? Okay, well, I'll make that more concrete by looking at so to make this more concrete, you can, so why are double categories the natural place to express the theory of categories? Well, this is sort of analogous to the fact that, like, a general place in which to express the theory of monoids is a categorification of a monoid, namely a monodal category. A general place in which to express the theory of a commutative monoid is a categorification of that, which is a symmetric monodal category. The natural place in which to express the theory of categories is the categorification of a category, which is a pseudo-category in cat, which is a double category. So let's actually write that. So let's see, though, like, how that works. So, like, if we have a double category D, then a category or a category object in D. And some people people call this all sorts of things. Some people call this a monoid in D. Some people call it a monad in D. I don't know. I'm going to call it a category in D for the purposes of this talk. So it consists of an object X and a pro arrow, from X to itself, and it consists of two cells. There's a yes, I called that M, but I think I want to call it R for now. At least. So there's a composition, and there's a unit. And these need to obey the category axioms. So you can express an associativity and the unitality laws using the composition that is available in the double category. So you can express, so now let's see how, so notice that these cells are globular cells, so their arrows are identities, their bounding arrows are identities. So you could do this equally well in a two category. So far the double category is not really doing anything for us, but from the perspective that I was saying, it should be fairly clear why you want the arrows, because those are the things that are going to give you the mappings between objects. So let me, I guess I'm getting a bit ahead of myself. So I guess what I should be saying is that sort of for us, the prototypical semantics in which we will look at double theories is going to be the double category of spans. So this has as object sets, as arrows functions, as pro arrows spans, and as cells morphisms of spans. And I guess it's kind of conventional to name double categories after their pro arrows. So this is span. So in particular, a category in span is just a category. Some other kinds of ones that are nice to look at are like, some other nice choices are like D is the category of spans internal, it's category of spans in some ambient category S with finite limits. A category in span of S is a category internal to S. And similarly to that, another very nice one thinking about is V matrices for V a, well, so let's say that we'll want, to make this nice, you want various things on V, but like just to, it should be, let's say, a symmetric monodal category with coproducts over which the monodal product distributes. And then a category in VMAT is a category enriched in V. So one nice thing about all this is that once you've got the right structure, we'll be able to get, so you get sort of for free internalized and enriched definitions of monodal categories and like all of the various theories that we'll be able to express. So that's kind of cool.
Those object sets.
Yeah, okay, so so VMAT has, let me, objects are sets, the matrix, the pro arrows are matrices, but the weird kind that are not, that are like, well, it's like the fancy kind of matrix where the rows are set times set, yeah. So it could be, it's like a very, very big matrix, yes, but it's a matrix, yeah. Right, and then a cell is a family of maps in V indexed by the pairs of for like the rows and the columns. Yeah. Right. Okay, so getting back to where I was previously here, though, if I have some category objects, x are mu eta, and let's say y, consistent with my own notation, s nu. So if I have two different category objects in D, then a functor, let me give these names. So a functor so here's where we're going to need to here's where we're going to want to start to use the fact that our cells are not just globularly shaped. So this will consist of an arrow from x to y and a cell that looks like, oops. So you can recognize in this the object part of the functor and the arrow part of the functor, and then the fact that like the basic functorality requirement that like those maps be compatible is encoded by the fact that phi has f and f is its boundary. And then this needs to obey, I won't write. Yeah, that's my bad version of a phi, which is supposed to be like Greek f, so it's supposed to go with f, but apparently I can't draw phi. So this is.
I think generally the dash is more vertical.
Okay, well, now is not the time for me to try to learn how to draw phi. So obeying the functor axioms. Okay. And you can also express a natural transformation in D. So we've got categories, functors. You can talk about natural transformations in D, which maybe I'll just say so. I'll just say that the data for one of these is a cell that looks. There are actually two different ways to describe it. So the most intuitive one is to take something that looks like this. Oops. And at least if you look at the these cases, you can see that this is at least giving you the right data. Like in the case of span, you get a pair of maps indexed by objects of the top category and maps in the bottom one. So right, so all of this stuff wants to live in a double category, which is a good initial sign that this is maybe a place that we want to be formulating these things.
But
yeah.
Doesn't R need to be involved in natural transformations?
Yeah, so I just wrote down the data.
Okay,
so
okay, that's fine.
Yeah, but it is there. It's definitely showing up in the axiom,
Yeah.
which I could write down. Would it be helpful to write down? I'll write down, since there is a question. May as well. It's good to see how you can express these things. Yes. This is alpha. So then I have So my other functor is G E. So, and then I need to, so so I've got two S's here, so I need to apply the composition in my codomain category. Okay, so this is equal to sense? Yeah. So this is like an expression of the usual naturality axiom.
There's a question.
Yeah.
The tops of those are only kind of
Yeah. So
equal.
yeah.
Like a general strategy for dealing with that.
Well, my general strategy is usually to when writing down these things, to exclude the associators and uniters involved in the double categories. So so in general, so it is worth saying this, that all of these double categories are genuinely pseudo, but it's really a pain to write down these
But there's
things.
nice- You could put it.
I could.
You could put an R over both the top.
Yes, you absolutely could.
And write uniter on both sides.
Yes, you could, and then it would be great. But I'm generally not, because then it gets really annoying as the equations get bigger and stuff. So it's also worth pointing out that there is a strictification theorem for pseudo double categories, which generalizes the one for monodal categories. So you can appeal to those sorts of things too if you want, I guess. But, really, you should just sort of imagine that they're there. Okay.
And real quick.
Yeah.
And if you've never thought about this, please don't feel compelled to
Yeah.
do so on the spot.
Yeah.
But when I'm looking at the form of this definition of natural transformation as a square from the identity on X
Yep.
to our span of morphisms on Y.
Yeah.
I'm wondering if you were to say, reverse the roles and put R upstairs and IDY on the bottom. And
So I see what-
similar axioms.
So I see
That
what.
is something.
Yes. So I have thought about this, and I was debating about whether to talk about it. And so, since you ask, I will. And because so this is the description of a natural transformation you would write down if you are just going based on what is a natural transformation, how is it usually described in ordinary category theory. This is not, however, the description of a natural transformation in a double category that sort of emerges most naturally on its own. So that one is, so there's an equivalent definition that is more symmetric and that does kind of appear later, we'll see. So it's actually important to know this to be able to recover the definitions that you want. So is the data is a cell now, as you said, Brandon, that looks like an R upstairs. Call this alpha bar, and so it needs to obey.
Is that square meant to be the same as the ones above it?
Yes. So right. So how do you pass back and forth? Given one of these, you define alpha bar by either side of this. Given alpha bar, you
Compose with the unit.
yes, you precompose with the unit. And then there's an axiom. If you want to start from this as your basic definition, there's +2 equations that this needs to satisfy. It-
The two definitions like mates or something.
yeah, I don't know. I don't know.
I've seen a definition of natural, like a,
Yeah.
what's the word? Concrete definition, non-double categorical definition of
Yeah.
natural transformations that corresponds.
Yeah, so if you cache this out in span, it's going to say that a natural transformation is for every f c to d in C, I get a map from f c to g d. So the data is now indexed by morphisms rather than, and then like the equations are that like alpha f composed g is the same as like alpha bar f g g or f alpha. So this is another way to define a natural transformation, not the one people usually use, but it is the one that actually is the most symmetric and it emerges most naturally here.
This is actually different from what I was at. I was asking if
Oh.
something happens when you keep the R upstairs and have the identity on the bottom. This,
Well,
that's probably less interesting.
it's not so interesting because it's going to force like an equality down here.
Right.
In general, like what tends to happen is that it's pretty common to want to have identities upstairs, but non-identities downstairs, but not vice versa.
Thanks.
Yeah. Okay, where am I? So now I want to turn to, all of this is just supposed to create in your mind the impression that double categories are a natural place to interpret the basic notions of category theory. Now I want to talk about what additional structure do you want to put on a double category so that you can express various theories of interest. Because you can express these basic notions, but without anything else, like you couldn't like say what a monodal category is, right, in an arbitrary double category. So let me now start to talk about that. So the short version is that I want to say that a double theory, terminology work in progress, is a Cartesian equipment. What is that? So basically, this has two components. It is a Cartesian double category. So in other words, a double category with finite double categorical products. And it is also an equipment. People use all sorts of different names for this, aka a framed bicategory, aka vibrant double category. There are yet other names people have used as well. And I'm not going to go into like a ton of detail about like what these are, because like to spell it all out would take quite a while. Instead, I just want to say what you can do in them and why you want them. And then so a Cartesian double category is, roughly speaking, it has, you have a Cartesian category, you have a Cartesian structure on D0, and it's also, so in other words, both of the underlying categories of this double category are Cartesian. They are so in a compatible way.
So the product of two pro arrows has as its source the product. of
Yes.
the two sources.
So I'll give like there is, I guess, in the case of, there is like a nice slick definition that you can give of this, which I'll give, but and then I'll only unpack it like a little bit. So, right, so like, I guess, right, so so that is true, David. So D is Cartesian if the diagonals double functor and the terminal one have right adjoints in the two category of double categories, of pseudo-double categories, pseudo-double functors, and vertical transformations, which I'll just call natural transformations, double functors. So what this says is that you've got some double functors so you have double functors, so in particular you get so in other words, what can you do if I have like two cells alpha prime, let me try this. So you can say like, if I have x, m, y, and then I have a primed version of one of these, I can take the product and the products, these give you underlying Cartesian products on D0 and D1, but because these are double functors, they're all compatible. So like I can do stuff like this. Right? And then basically there's also like duplication and deletion, because the structure is Cartesian. Those are also like kind of compatible with each other, and that there are variants like coherence axioms that like tie them together in the horizontal direction. Yeah. So, but it's pretty intuitive. Basically, what we're saying is that, like, you know, if I'm going back to this type theory perspective, I can take products on the objects and on the pro arrows in a compatible way, and then I can also take products between the maps. Yeah.
So if you take x to x times x by the diagonal,
Mm-hmm.
and y to y times y by the diagonal, you take m times m prime along the bottom, and then you pull back, do you get a local product?
I do believe that Cartesian equipments have, I don't know if just, I know that in Cartesian equipments at least you have like local products in the horizontal by
Okay,
category.
you probably get them the way I said it.
Yeah, and you probably get them the way you said.
Okay, cool.
Yeah. Yeah. So, I mean, there's a bit of a tangent, but like, yeah, Cartesian equipments are nice because the definitions are simpler than things like Cartesian bicategories, but like they give rise to those. Yeah. Okay. So So this is just the double categorical analog of like algebraic theories having products. There's nothing too crazy going on here. So what's this other ingredient? Being an equipment. This is sort of new here. There's no analog of this in the setting of algebraic theories. So what is this doing? Well, let's think about this. So if we have, let's say that we, let's see, let me find my, well, actually, okay. So the idea is that, let's say we had our, we have like a, how do I say this? Okay, here's an example I want. So we're going to want to be able to formulate the theory of like a Cartesian category. So in other words, like a category with chosen finite products with like a pairing operation that, you know, the usual equational description of a category with finite chosen products. And so in order to express the pairing operation, you need to be able to say, you need to be able to describe the type of having two morphisms with the same domain. So you could start, so let's say that like you've got your Hom type, right, is like this, like we've been discussing. So, you know, you can form Hom squared using the product structure. So then this will be like the type of a pair of two different morphisms. How can you then say that, how can I then get a type that represents two morphisms with the same domain? I need to be able to do something else. What I need to be able to do is say, I can start with this, but I can pull back along the diagonal to get some new thing. So, which I'll denote delta x bang r squared, and then there's like, this is a restriction. So in other words, I can take this type and restrict it along its domain via the duplication map to get a new type that represents a pair of morphisms with the same domain. And so in order, so you want to be able to do things like this, and an equipment is the sort of structure in which you can do that. So the slick definition of an equipment is that is a double category D where the source target pairing functor, so this goes from D1 to D0 cross D0, is a fibration. So basically what this says, so it says that if you have a niche that looks like this, then you can fill it to form a, you can get a pro arrow upstairs and you can, and then a cell. And this satisfies a certain universal property, which essentially says that like this cell is sort of like terminal amongst other fillers that can put morphisms here and here and then a cell. You can factor all of those through this. I can write that down, but I think I'd like to keep going. The point is just that like there is a universal way of doing restrictions. And so that's why I want those two structures. I don't currently have like a principled reason for saying, besides my list of examples, for why this should be what it is. But that's my reasoning so far on that. So now I want to turn to the next big sort of thing, which is, so I guess I should have said this is us. Theories are always small. This is like a small Cartesian equipment, and then it's usually convenient to also make it strict because you can do that. Now we want to talk about models of theories, and because we're in the world of higher dimensional categories, you have choices about what kind of functors you can take. You could look at pseudo functors out of your theory. So from my theory to my semantics, where, for example, by default, let's say it's span. But you could also take lax ones. And at first, I was reluctant to use lax functors because lax functors contain a whole lot of data, and they can have the property that that you can have a finitely presented theory that needs a generic lax functor can require an infinite amount of data to give you a functor, because like the laxsters can pack so much information. So I was initially sort of reluctant to want to go there because I'm a very sort of like computationally minded kind of person that likes things being finitary and stuff. But I eventually was persuaded that actually lax functors are really the way to go, because the concept of a lax functor contains within it not just the notion of a category, but of the notion of functors, natural transformations, and also profunctors. So like all those internalized definitions that we saw earlier, every one of those is already implicit in the concept of a lax functor. And so that's what I want to explain next. Yeah?
So here you have like HOM as a non-identity error.
Yes, that's because I haven't yet gotten to lax functors. Yeah, so that's coming.
And lax functors are product preserving?
And we'll also need to talk about what they do with products and the equipment structure. They are product preserving, and the situation with equipments is a bit more subtle. I'm currently sorting that out. I haven't yet figured out whether I need to, whether it's enough, whether an extra condition is needed. It's a bit subtle. So,
Span's also equipment,
yeah, yeah. So my main examples spans in, an ambient category S, VMAT for suitably nice V. All of those are Cartesian. When V is Cartesian, VMAT is a Cartesian equipment. So like, yeah, it's pretty nice.
right? You could ask, there's a way to ask that a lax functor preserves equipment structure.
There is, but you have to be, you don't just want to say something like it preserves like companions and conjoints, because then you force it to be normal. So yeah, but let me make it a little more, we can come to that.
But it doesn't force it to be pseudo.
It does not force it to be pseudo, but we'll soon see why we do not want our lax functors to be normal, because we're gonna really use all the goodness that comes in a lax functor. Okay, so I'm going to take some double categories D and E, and I want to at least sketch out the definition of a lax functor. And as usual with this sort of stuff, like the definitions get long. Mainly what I'll do is I'll tell you I'll tell you some of it. Basically, we're going to have a lax functor. So we're interested in lax functors from D to E, and it consists of, well, as usual with double categories, you always kind of start by just taking the corresponding thing on the underlying categories. So I have functors. Oh, sorry. Thanks. Thanks. Yeah. And then these commute with the source and target. So those are compatible with each other. And then, so then what makes it be lax is that you have, four composable pro arrows in D. For every pair of these, you have a laxator, which is like a special cell that looks like this. So rather than just saying that it's directly associative in the horizontal rather than saying that it's strictly functorial in the horizontal direction, you instead just get like a comparison cell. And so if you've seen the definition of like a lax monoidal functor, this is a generalization of that. And also for objects in D, there is a uniter which looks like this. Okay, so in particular, f of m compose n is not necessarily the composite of this, and f of the identity is not necessarily the identity. And at first that seems weird, but what's really cool, okay, so this is the data plus axioms, and those axioms are very like quite analogous to the ones that you have for a lax monoidal functor, and in fact generalize them. So what I want to explain, though, is what this lax double functor is packing. So and this is a standard fact. So on the one hand, for every object in D, you get a category object in E whose carrier is basically the image of the identity at X under F. And the composition is the laxator at the identities. So I'll write F underscore XX. This is a shorthand for like F id X, comma, F id X. And finally, the unit for this is the uniter. So this is a category in E, similar to what, like, following the definition that I gave earlier. For every arrow in D, I get a functor and for every cell of form, let's say, let me change my orientation. Does this stand in the way? I get a natural transformation in E by applying F. So you'll notice that when you just hit this cell with F, you have F id X on top and F id Y on the bottom. Which is the alternative form of the natural transformation that I gave. So that's why I said that, like, that's the version of natural transformation that, like, double categories want to have. And actually, we haven't talked about how, so pro arrows also give rise to, like, pro functors internal to E, but for now I'm just focusing on the two categorical part of this story. So that's pretty appealing because it means that, like, if we want to talk about categories with extra structure, we're constantly wanting to talk about natural families of maps, and we're constantly wanting to talk about operations that are functorial and so forth. And that is just built into what a lax double functor wants to be. I'm about out of time. I think what I will do is just I want to conclude by at least giving an example of a theory. So let me sketch one of those, and then we can wrap up. So, I'll call this an example, actually. So the theory of pseudomonoids is so it's a Cartesian equipment that's generated by, we've got an object X, arrows for the tensor in the unit. There are there's an associator cell that looks like this. So when I use juxtaposition in these pictures, this means Cartesian product. So and there are unitors, uniter cells, so these like this. So this is going to be the left uniter. And there's a right uniter. So, and then we also need generators that will serve for the inverses, so plus alpha inverse, lambda inverse, rho inverse, subject to the two classic equations, which I will not write down in their full glory, but axioms that correspond to the pentagon identity and the triangle identity. So it's worth pointing out that this theory only uses cells that have trivial pro-arrows. So in that sense, you could also represent the theory as a two-category. But the double categorical setup will actually give you the right morphisms between the models of this theory. So the last thing that I want to just allude to in my final minutes here is, part of my motivation for this whole thing is I don't just want to get a category of models. I want to get a full two-category of models, and you can do that using the higher dimensional structure that you have with double categories. So in particular, there is I believe, a notion of, so there's certainly a notion of natural transformation that would recover like strict monoidal functors, but there's also a notion of lax transformation, which will give you lax monoidal functors as morphisms. And there's a notion, a certain specialization of the notion of a modulation will give you monoidal natural transformation. So there's a whole sort of picture there to be that you can build up, the details of which I'm still working through certain things. But basically, I do think that it can achieve what it's supposed to, which is that you can get the right morphisms and the right two morphisms, for these different kinds of theories, with a choice about whether you want the models to be, strict or pseudo or lax. So I'll stop there. Take questions. Thanks. Yeah.
So, classically, categories are functors from, or lax functors from the single object double category to span.
Right.
However, the single object double category, I don't believe is a Cartesian equivalent.
It is in a trivial way.
Oh, okay.
I think. Well, it's certainly a Cartesian. It's a Cartesian double category in a
You
true.
don't want to preserve the Cartesian structure on that. You want to have a fresh generator so that you don't have to.
You're right. You're right. That's true. You're right. You want to. Yeah.
So, yeah,
You want to take the Cartesian equipment freely generated by one object.
right.
What is that?
Yeah, yeah, exactly, what is
Is
the?
that natural numbers of many objects? Is that?
Yeah, I don't know if there's a really slick way to say what it is, but that's an interesting
It is
question.
finite span.
It could be thin span. It's a good thing to.
Why would there be horizontals?
Because of the equipment structure, companions and conference.
Hmm.
Right, there you go.
Well, yeah, I'll have to think about that somewhere. But yeah, that
I think it might be that.
it might be. Yeah.
Which would be very nice for us.
Yes.
That was going to lead into a question I was.
Yeah, go ahead.
Was if you have like a category in the vertical direction, do you know how to take an equipment freely generated by it?
Yeah, so I don't have good descriptions of like those kind of free constructions. Like by general nonsense, like you can probably know that they exist, but like I don't. And so
It would be nice if it
It-
was found
yeah.
in that category.
yeah, but yeah, I definitely think it bears. These are all good questions of, in nice cases, can you give a crisp description of what those things are? Yeah, I don't know.
The reason I'm interested in that is because it would be nice, like, I don't know how, I'm not super familiar with literature on this,
Yeah.
but either in the literature or in folklore, there's a notion of two Lawvere theory, where you have like, a freely generated Cartesian two category and you take models in cat. And if you have a category, if you have a two category regarded vertically as double category, like your example, and you take models of that in cat, that ought to be the same thing.
Yeah, so
You're taking lax functors from that.
Exactly. So part of what I have to check is, so Schulman proved that lax functors preserve restriction cells. So that's good. Which is sort of not, I mean, it's not obvious immediately that's the case. There's like, you have to like think about that. Lax functors do not preserve companions and conjoints unless they're normal, but you still have to worry about the fact that like by sort of right, because equipments have this alternative description in terms of companions and conjoints, there's also a dual notion of extension to restriction. And you can always form those things, but but lax functors don't necessarily behave well with respect to extensions. And one of the things that you've got to worry about, and which I'm trying to sort out the kinks in, is like you do not want those extension cells, which are there, to be giving you extra junk in your lax functor. That's, I think, kind of getting to your question, right? Of like, you want to make sure that if you take the two theory and freely extend it to this thing, and then look at the right notion of structure preserving lax functor, you had better get the right class of models and not have some like extra junk floating around in them.
Right, whatever it is, I would want it to have the property that functors from the two category cat that preserve products correspond to whatever preserving lax double functors
Yeah.
from the thing you get into span.
Yeah.
Yeah.
Yeah, so they should definitely be Cartesian lax double functors, and then there's this question of what to do with the what if anything needs to be done to make sure the equipment structure is properly respected.